In this video, we'll talk about taking powers of complex numbers and what that might look like geometrically. So we know that multiplying complex numbers is really easy in polar form, right? If I have complex numbers r e to the I theta and s e to the I phi, it's super easy to multiply these numbers, right? I just get r times s e to the I theta plus phi. All the rules work like they should. The products work right, the exponential rules work right, so I can really easily multiply complex numbers this way. What does this mean for taking powers of a complex number? If I want to look at the number z, which is r e to the I theta, I can look at z squared. It should just be z times z, so it should just be r e to the I theta times r e to the I theta, which by our formula above is just r squared e to the I theta plus theta, or r squared e to the I times 2 theta. And the same is going to hold for any other power we want to do. If I want to look at z to the fourth, I just do this twice, or I think about it in the same way. Okay, this should be r to the fourth e to the I 4 theta. And in general, for any positive number, z to the n can be written as r to the n times e to the I n theta, for z being the complex number, r e to the I theta. So powers are super easy to find, provided I write the number in polar form first. I can just work it this way and it works out great. What about negative powers? Well, thankfully, these also work in the same way. So let's start with going towards z to the minus 1. Let's look at z bar, right? Z bar, the complex conjugate, was our main way of getting to what this 1 over z looked like. So for z being r e to the I theta, which we know is r cosine theta plus I r sine theta, we know that z bar is r cosine theta minus I r sine theta. But based on the even and odd properties of sine and cosine, this is the same thing as r cosine of minus theta plus I r sine of minus theta, which is just r e to the negative I theta, or I negative theta. You can also visualize this because the complex conjugate flips over the x-axis. So the complex number here, its conjugate is flipped over the x-axis, so its conjugate would be down here, and that's actually just the negative angle that would have given me in the first place. So for any complex number, its conjugate in polar form just has the negative theta on it. It's negative exponent in that form. So what does this mean? Well, this means then that 1 over z, which is z bar over modulus of z squared, becomes r e to the minus I theta over r squared, because r is the modulus of z in this case. And so I get 1 over r e to the minus I theta, which is r to the minus 1 e to the I minus 1 theta. It's the same rule from before, just with negative ones in there instead. So similarly, if I were to look at z to the minus 2, I could write this as r to the minus 2 e to the I times minus 2 theta, because I could go to z to the minus 1, which was with ones, and then square it. Now basically we have that for any integer power, this all works the same way. Having the same generic formula as before. What does this look like geometrically? Well, we can think about this in terms of just products first, and then go on to powers from there. The fact that r e to the I theta times s e to the I phi is r times s e to the I theta plus phi basically says when you multiply complex numbers, you do two things. You multiply the moduli, as in the r or s becomes r times s, and you add the angles of rotation. If I were to have two complex numbers, this one and say this one, and I wanted to multiply them, well, I'm just going to add this angle to this angle to give me something that goes a little bit further, and so is like over here-ish. And then I'll multiply the radii to give me somewhere way out here, z times w. Add the angles, multiply the radii. This works the same way for powers as well. I'm again just going to have a modulus that's that power of the original modulus. And then my angle is just n multiples of the original angle that I started with, in either the positive or negative direction, depending on if I'm going positive powers or negative powers. For example, we're going to compute z to the minus 1, z squared, z cubed, z to the 4 for the complex number z equals 1 minus root 3i. Now, you could work this out by hand if you wanted to, but it's probably easier to convert this to polar form, do all the powers that way, and then convert back at the end. So polar form here, r is going to be the square root of 1 squared plus root 3 squared, which is square root of 4 or 2. And theta is going to be the inverse tangent of root 3 over 1 with a minus sign, which is going to be negative pi over 3, which is in the fourth quadrant, which should be correct here. So my z can then be written as 2e to the negative I pi over 3. So what does this mean? This means that z to the minus 1 is 1/2, or 2 to the minus 1, e to the positive I pi over 3. This means that z squared is 4e to the negative I 2 pi over 3. Z cubed is 8e to the negative I 3 pi over 3, or pi. And z to the fourth is 16e to the negative I 4 pi over 3. Just multiplying the angle by the number that I'm raising that power to. Now we can convert all these back into rectangular form. We know z was 1 minus root 3i. Since cosine of pi over 3 is 1/2 and sine of pi over 3 is root 3 over 2, this is 1/4 plus root 3 over 4i. And we do the same thing for all of these. Cosine of minus 2 pi over 3 is negative 1/2, and sine of minus 2 pi over 3 is negative root 3 over 2. So I get a minus 2 minus 2 root 3i, because that should be in the third quadrant. For z cubed, I know that e to the minus I pi is minus 1, because I'm going to be at pi, which is the angle going straight in the negative direction. So this is just going to be minus 8. And then negative 4 pi over 3 is the same as positive 2 pi over 3, so I'm up in the second quadrant. So I'm going to get a negative 8 plus an 8 root 3i. So you guys could do a little work to go back to the rectangular form once you have the full form of these powers, but it's probably easier than writing out z and computing it to the fourth power manually. This will go a lot quicker than that fact. That's the idea of powers of complex numbers and how they work. When they are in polar form, it's really easy to figure out what these powers should look like. You have to play with the angles later on to get them back into rectangular form, but it's a lot easier than doing it the other way by just trying to raise things to powers over and over and over again.